Hello, everyone. Thank you so much for joining in. This is my first time speaking at KubeCon. I'm slightly nervous, but also incredibly excited and grateful to be here. Thank you so much for joining in. A quick introduction. Hi, I'm Ria. Thank you. Hi, I'm Ria. I'm currently working in the fintech industry. Over the course of my career, I worked with multiple database systems, backend technologies, and recently have started diving into the world of DevOps and cloud-native tools, and it's been an amazing learning journey so far. What really drives me is making sense of complex things, breaking them down into easy, understandable bits, and then sharing my knowledge with the community. I'm also very passionate about organizing outreach initiatives, especially for women in STEM. And in my free time, you'd either find me jamming to my musical instruments or just reading a good book. So, do you remember your first deployment? I was there too. The joy of seeing your pods running, your services being connected, your app being live. And I remember thinking, wait, that's all it takes for Kubernetes to deploy your application. Just pure declarative magic. You tell it what you want, and it will handle the rest. And naturally, I experimented more, deployed more stuff, learned all the fancy tools, but then I hit a wall. Now, I wanted Kubernetes to do something different, something dynamic, and I was not sure how to do that. It was one of those moments when the pieces of the puzzle are right in front of you, but you just don't know how they fit together. And that is where this story begins. So, what should you expect from today's talk? This talk is not another code walkthrough or a tutorial, but it is my personal journey of figuring things out step by step, making sense of them. As the title might have revealed, we would be talking about custom controllers and CRDs, but the purpose here is also to peel back the layers and understand what's happening under the hood and why it matters. As I take you through some of the fundamentals, some tools that will help with development, and some best practices that I picked up along the way, I really hope that by the end, you're not just comfortable with how controllers work, but are actually excited to go home and build one yourself. So let's get started. Back to my problem. Now, I wanted Kubernetes to do something dynamic. By default, when you create a deployment, it starts up your pods, and that's it. In order to make those pods reachable by internal services or by external users, you manually add a service. Of course, tools like Helm can help, but they are static. They're not really responding to what's happening within your cluster, and sometimes that's exactly what you need. In real-world platforms, like in the fintech industry, there could be a need to spun up short-lived workloads created by different teams, spun up on demand with varying requirements. Could have different labels, annotations, routing needs. Now, to tailor to that, a service is required, a custom service that if the workload changes at runtime, the service should adapt to it. It's also not just about connectivity. The service should also be platform compliant, should follow the platform policies like proper naming conventions. Now, something smarter is required, something that could watch your cluster, understand the state of the deployment, and just create a matching policy compliant service for that. Of course, you could extend this idea to adding TLS certificates, network policies, ingress rules, but for the purpose of this talk, let's keep it super simple. If a deployment occurs in your cluster with a label set to auto-service as true, a service should automatically be spurned up, no manual intervention. If at runtime, this label is set to false by a human user, by some other process, by a CI/CD pipeline, the service should be cleaned up. Now, I was not sure how to do this. And like many engineers, my first instinct was, let's write a bash script. And it worked. Now, I queried the API server, got all the deployments with that particular label, and created the matching service. I was really happy. Slept for 30 seconds, and the job was done. And then things started to fail. Firstly, this was not reactive. If something got changed, got added, or deleted within those 30 seconds, my script simply missed it. If the service creation failed, I was not really retrying currently in my logic. I had to handle the cleanup of services if this particular label changes to false. There were race conditions. I was working with the deployment, but its state changed in the cluster. Maybe it just got deleted. I was polling the API server every 30 seconds without even realizing if something has changed or not. And finally, if some error happened, I was not sure where the problem occurred from. There was no logging, no visibility, and I was sure that I needed a better script or just a better approach. Thankfully, I stumbled upon this phrase, that everything in Kubernetes is a controller. So till now, I had been deploying, experimenting, doing fancy things with Kubernetes without even realizing what's happening under the hood. What really happens when you create a deployment, say, to spin up 2 pods? You write your deployment YAML, give it to the API server, and your intent, the deployment, is stored in the etcd. Now, the controller manager has a bunch of control loops running. One of them is the deployment controller. It notices this deployment and creates a replica set. Job done. Now, the replica set controller notices this and spins up 2 pods. Why 2? Because you had specified in your YAML that you needed 2 pods. Nothing was running currently. Replica set controller brought your system back to the desired state. The pods are scheduled in the pending state with no node name attached. The scheduler, also a control loop, notices this and assigns a home to the pods. Job done. The kubelet running on the target machine notices this, that, oh, hey, this is where I'm running. Let me get the image. Let me start up the pod, bringing the system back to the desired state. Now, if something crashes, the kubelet updates the API server that the pod has crashed. The replica set controller again notices this, that there's a mismatch. User had defined 2, but only 1 is running. I need to bring the system back to the desired state, and job done. So you see, these control loops is what is powering Kubernetes. Watching a particular resource, taking some action, reconciling it, and bringing the system back in line. And this is the exact pattern that I could also use for my use case. I don't have to work around Kubernetes. I could write my own custom controller. When the deployment occurs, the native controllers would do its job of spinning up the pods. But if this deployment has this particular label, auto service set to true, then my custom controller would also notice this and create a matching tailored service. From here onwards, the control is back to the default Kubernetes mechanics plane, and they would treat this service object like they would with any service object and establish the connectivity. If at runtime the deployments label is set to false, custom controller again notices this and removes the service. Service removed. Okay, so I'd be writing a custom controller, but where to start the learning journey from? One thing was clear, that I need a client to talk to the API server. Let's start learning from the one that we all use, kubectl. You use kubectl to write your deployment YAML, give it to the cluster, and your pods are live. Have you ever wondered how your client is actually interacting with all these resources that's in the etcd? Okay, so if you run kubectl apply.yaml in a verbose mode with this flag, you get a much detailed output. So you see, first it loads up the kubeconfig file to understand where the API server endpoints are. Once it knows the location of the server, it can talk to it, right? So it authenticates itself, and then it sent a GET request to this URL. What this URL has is that the name of the deployment. It's trying to create a deployment resource with name kubecon. That is what I was trying to do. It's not there, so it sent a post request to actually create the resource. What this tells us, that the API server is nothing but just a REST API exposing a bunch of endpoints that our client is interacting with. You can run it yourself. You run kubectl proxy, starts up a local proxy server, and curl that from a different window. You would see all the API paths showing the API group and the version. But how was the client able to figure out the entire path, the entire URL? Let's go back to the YAML. When you define your YAML, you always define these 4 fields: the API version, kind, metadata, and spec. Seems like these are not just for YAML formatting, but are the fundamental building blocks that helps Kubernetes understand and route your object. Behind the scenes, all these native types, pods, services, daemon sets, replica sets, stateful sets, are defined as Go structs in the Kubernetes code base. Like over here, you could see the type for deployment, the Go struct defined for that. And it always defines the type meta that has the kind, the type of object that you're trying to create, and some group and API version where this object belongs to. Metadata, name, namespace, labels. Spec, your desired state, what this object represents. For example, in case of deployments, this is the replica. Pod containers, the status, the actual observed state of your object. For example, the spec could be thought of as the items that you have purchased, and the status is like the tracking URL. Okay, with this in mind, let me give you a simple mental model that will bring everything together. Now, if you think of the API server as this librarian or this in charge of this well-organized library that has a bunch of groups. These are your API groups like core, apps, RBACs, networking. Within each of these groups, it is managing a catalog of items called as resources. Like within core, you have pods, volumes, services. Within apps, you have deployments. Now, if you want to create or retrieve a book of kind novel, if you know the group version and kind, you can trace the exact endpoint you would like to talk to, where exactly this book would go. Similarly, when your client is submitting the YAML, it's not blindly submitting it. You have specified the apps, the group version and kind. The client is smart enough to map it to the underlying resource and construct this URL for you that has the group version and resource. Once you have that URL, it reaches the API server with your payload. The API server, we know that the Go structs are already defined. The schema is derived from that. The API server validates your object against that schema. Just like your librarian would check that the book that you have sent has the right title, the right dimensions, the right number of pages to be classified as a novel object. Once that's done, it's safely stored in the cluster. So you see, map kind to resource, construct the URL, and the endpoint is the end bit, actually. You talk to a resource by just that endpoint. Now, if I actually want to introduce something new, something whose endpoint is not available in the API server, like bringing this mental model to life, what if I actually want Kubernetes to start recognizing this kind novel as its own object, like creating a custom resource, adding a new shelf in my library, like books.io, a group, and giving this novel my own set of properties. So when you're creating a custom resource, you're using custom resource definition. I think of it like a form you fill and just submit it to the API server. It will handle the rest. Now we have seen that there are some properties that you need to define to be able to make API server understand your object. So the group, version, the schema, how this object would look like. Here I'm just defining the title and the pages, that it should be, it should always have a title. The pages, I'm adding a simple validation rule that it should be within 1 to 500. If it's greater than that, API server would reject it. And of course, the kind novel. And also, the plural is the resource name here, the resource which it would create with. You submit it to the API server. It exposes 2 endpoints for you to interact with. Now, the next time you create a novel object, the client, kubectl client, is smart enough to update its internal mapping. It knows that there's a new kind in town, and you're able to talk to this endpoint. So you see, your custom resources or your built-in resources are being accessed in the same manner with the same set of verbs, whether it's create, delete, get, list, update. All you need is a way to reach the endpoint and the verb, the CRUD operation you would like to do on that resource. Okay, programmatically, what's happening is it's using the client Go library. So kubectl, your controller clients, is using the client Go library. That's the official Go library available. It offers us 2 types of clients. One is a type client. Now, these are like pre-defined client sets for every kind. There's no mapping involved. When I'm using apps v1.deployments.get, I know that I'm dealing with a deployment resource, and I'm able to resolve that URL. Using this It's just using the statement over here, client-set.apps v1.deployments, is just under the hood making that endpoint that we need to talk to with the get keyword. And these are backed by the Go structs because they're already defined, so they are strongly typed. The compiler knows that these fields would be there in my object, so it can safely do .spec.replicas. Or if you just like to talk to any object, you could use a dynamic client. The clients which are not backed by Go structs, like your CRDs that you just created. All you need to do is give your group version and resource here, and it would work in the same manner, construct that URL, and let you interact with the resource. It's flexible, but you lose the compile time safety. You're essentially parsing JSON over here, just dealing with the raw JSON output and extracting and parsing fields yourself, just like over there. But it's great for custom resources. For custom resources, you could either generate your own type clients or use a dynamic client. With this, I think we have enough information to start building our controller. We are watching an inbuilt resource. We are interested in watching the deployments. So let's start building the controller. We would be using a type client set. Our learning from kubectl, we first load in the kubeconfig file to get where the API server is and authenticate itself. Us as the client, I'm building a Go controller now. I'll specify the client set that I need. So from the client Go library, I take out the type client set, and I am trying to list all the deployments. So this syntax, apps v1 deployments, GVR, and the list. I'm trying to list all the deployments that are in the cluster. List is great. List gives you a list of all the deployments that are in your cluster, but it's a one-time view. Post this, the connection ends. If something changes in your cluster, you have to run a list operation again. This is very similar to you polling the API server again and again. We need something smarter, something that could tell us as and how the events are happening, live updates. For that, you use watch. Now, watch keyword opens a long-lived connection, and the events are streamed as and how they are happening in your cluster. So the events look something like this, that they have the type, what has changed, add, mod, modified, or deleted, and the actual object. And this is exactly what we need. It's like tuning into the radio and getting the updates from that point in time. But what if something changed just before that, just before I start watching? So I need a way to get a place from where I should start watching. Something like list, getting the state of the cluster, and then from that point in time, I start watching. Now you have your answers. You will list, watch, work on that deployment object, and create the service for it. But this is too manual, too low level. Client Go makes our lives easier, gives us informers, a higher level abstraction over list and watch with much less boilerplate code. So this component does not only do list and watch for you, it handles any kinds of disconnections that might happen while talking to the API server. It will handle that. It gives you a local cache and also handles resyncs. What they are doing, we'll discuss shortly, but overall, this would make our lives much simpler, so let's use informers. We'll use informers. It has the new shared informer factory that has a bunch of informers available. We are interested in watching the deployment, so we initialize the deployment informer. Great. We would also have an event handler attached to the informer. So remember, we would be getting updates from the API server as and how things are changing, add, modified, deleted. For every update, the consecutive business logic would run. So the business logic here is extract the label, check if it's true, create the service. Awesome. Now let's start our informers and wait for the cache to sync. All this is again abstracted away from you. Internally, what's happening, that there's a component reflector that does a list, gets all the deployments that are available in the API server, pushes it to a Delta FIFO queue, all internal, one by one. The Delta FIFO queue updates an internal cache. What this cache is, it's just a key value store where the key is the name and the namespace, and the object is your actual object. And then for that particular event, it triggers the event handler. In case of a list, it is treated as an add event, so the add logic would be treated. It does that for both of them. Once the cache is synced, the connection switches to watch. Now from here, whatever updates that we get would be pushed to the delta FIFO queue, updated in the cache, and the event handler would be triggered. Problem solved. But your event handler would be triggered just once for that event. If, imagine this was an add event and the API server was temporarily unavailable, so your add logic would fail. That is game over for this event. Informers do not give us an ability to retry that event. We have to make the system resilient. This is the same issue that we faced with our bash script. We were not really retrying. Now we need a way to retry that event if it happened because of a network blip or something that we want to retry to. So we'll add our own work queue. We add our own work queue, and now the flow looks something like this. You get the event, push it to the delta FIFO queue, it's popped from there, updated in the cache, and the event handler now, instead of triggering the logic immediately, adds the key to the work queue. A separate worker thread would pull this key and process it. The advantage, if anything fails, this can safely be added back to the queue for retry. And you can even add it back with a slight delay, just to give the system some time to not be in any hot loops and not overwhelm it, and retry this key with a certain delay. Now, this particular queue does much more than just adding resiliency to the system. It also safely decoupled event detection from event processing. Earlier, we were triggering our event handler for each and every event. Now imagine in a flurry of updates, maybe like 1,000 updates happened in 2 seconds, we would have triggered that event handler 1,000 times, even without realizing if some update was useful, was meaningful or not. This can become overwhelming for the system. It can introduce bottlenecks. Now, we are just safely enqueuing the key once and processing it calmly. The deduplication logic won't allow you to add the same key again and again. So you add the key once, and your separate processor thread takes this out, gets the latest state, the latest sync state from the cache. The cache is always in sync with the API server. So you're not really querying the API server, hitting it, burdening it. You are querying your cache, which has your latest state. Get the state and have a single reconciliation logic, which would bring the system back to the desired state. The goal was always to reconcile, look at the deployment object, and bring it to the desired state, regardless of the events, regardless to what led to this state. That's exactly what we are doing, and that is what exactly production-grade controllers do. One resync logic handling all the heavy lifting, regardless of the events and ignoring the noise. So we'll use a lister object to get the latest cache, the latest object, that is the current state of the object from the cache. And now we are left with the final piece of the puzzle, our control loop. Our control loop would be handling 3 things, should have our business logic, should be idempotent, and should also retry in case something fails. Okay, so now we have our keys in our queue. Separate worker threads pull the keys one by one and start processing them. So you extract the key, get the name and the namespace, get the latest current freshly synced state from the cache of the object. You have the object, then you check the label. If the label is not there or is set to false, that means that we don't really need a service for this particular object, for this particular deployment. If it's already existing, we need to delete that service. But if it's true, then we move ahead. So we first check over here, my name, the service name I've given is the deployment name appended by internal service. Let me check if this already exists. If it exists, the system is already in the desired state. I don't have to do anything. I can just forget this key and move on to the next one. But if it's not there, then you construct your own service object, the way you would define it in a YAML with your own set of properties, the way you want it for your deployment. You would extract the labels from the deployment so that the routing is correct. You can add your own ports, the type of service you wish to create for this particular deployment, clustered IP or node port, load balancer, all up to you. This is where your custom logic resides, and just create that service. If something fails, you add it back, add the key back for retry, else you just move on to the next one and start processing that. With this, we have come from a fragile bash script to something that's resilient, efficient, and Kubernetes native. Something that exposed your pods to the world. So the next time somebody asks who let the pods out, you know that it was your custom controller in this case. Now, this was just an MVP, with a use case kept intentionally simple and even the code snippets, just to make you understand the core components that are working behind the scene, powering your controller. From here onwards, you can add your enhancements. One of them being running this controller not outside the cluster, but inside the cluster. You have to do like a pod. You'll containerize this Go code, run it as a pod, and you'd have to do minor changes in how you get the kubeconfig file. You'll have to have a way to talk to the API server. Earlier, we were using the kubeconfig file. Here, you would be using in-cluster configs, having a service account, and giving it only those responsibilities or only those roles for the resources it can watch or query or create or delete. Limited set of responsibilities. Next, adding resync periods. So the informer gives us an ability to add a resync period to it. What that means is that time to time, your informer would pick up all the keys that are in your cache and just push it to the queue to reprocess it again, even if no change has occurred. Now, this is great just to ensure that no system drift has occurred, especially if you are dependent on any external dependencies. Maybe somebody deleted your service in the background. You won't get to know because you're not watching the service in this case. By a resync period, your deployment would be processed again, and that service would be created, bringing the system back in line. Observability. As you move towards more production-ready practices, you would want to have structured logs. If something is becoming a bottleneck in your controller, like your queue, you need to understand why it's a bottleneck. Is it that my reconciliation logic is too slow? Or is it that because there have been subsequent failures while talking to the API? Or it's just that the rate is too much and my controller is not able to handle that? All these are handled by different solutions, and metrics could be your gateway to understanding the performance and the health of your controller. And finally, testing it end to end, writing integration tests, unit tests to understand your reconciliation loop and how it's performing. With this, there are endless possibilities. Now you can have your own CRDs and create deployments on a fly. You could just specify in your CRD what kind of deployment or your environment actually should look like, the deployments, the services, it should have TLS, the volume mount. A custom controller would watch that and bring your desired state to life. And CRDs and custom controllers actually let you extend Kubernetes to its full ability. Now, as you add more domain logic to it, if your controller is able to take database backups or is able to scale up or down an application, you're not just building a custom controller, but actually an operator. Now, SDKs like Kube Builder make your job easier. Inside, it's still using the same components, same worker queue informers, but gives you all the boilerplate to do it with much less, with you focusing on your domain logic. And it also gives you type clients for your CRDs, making development easier. Now, writing a custom controller changed the way I view Kubernetes. It's not just a tool for me, but a platform I can design with. And once I started realizing that, understanding what's happening under the hood, I understood that these principles have solid reasons behind them. And with this, you can not only shape Kubernetes in your way, but also reimagine scenarios where you can make Kubernetes work for you. That is why understanding these were very crucial. Now, the next time you would see a Kube Builder scaffolded code or a reconciliation loop, you would exactly know what's happening behind the scenes. And you are ready to extend Kubernetes your way. Thank you so much for attending this talk. If you have any feedback for me, please let me know so that I can improve for my future talks. Or if you would just like to talk about books, tech, or music, please find me after the session, and I'm happy to talk about it. Thank you so much, and have a wonderful evening ahead.